Hello everyone, I hope you're doing well. Today I'm here to be presenting you basically a recap of what we did in section 2. So just as a heads up, all of the questions that we will be doing, the timestamps will be in the description below. So this week we're doing algorithm analysis, and so this is the worksheet. The link to the worksheet is right here, or you can of course go to our website and click on a blank worksheet. So we're going to go ahead and skip the logistics, and we're going to start with essentially basic big O. So just as a recap, basically from 143, we have a bunch of complexity classes, including constant, logarithmic, and so on. As you can see in the table here, as you go down, it has basically a worse runtime. For example, here, a constant runtime will be better than logarithmic runtime, and then so on right here. All right, so some basic rules that you may have learned from 143 is that exponentials dominate polynomials, higher order polynomials dominate lower order one. For example, n to the power of 4 will obviously dominate n to the power of 3 and 2 and so on. Polynomials will always dominate log, and log dominates constants. And we'll follow up with sort of the proof later on in the video. All right, so when we're analyzing these kind of things, it's important to note that we don't care about constants, because in all of these, we're going to be assuming that n is approaching infinity. All right, so for example, 750 million is minuscule compared to whatever n is going to be. All right, so first of all, we're going to be doing problem 1a and problem 1b, which is comparing growth rates. So what we're trying to do here is we're going to be simplifying this into a tight big O bound, and then we're going to be sorting them from the fastest growing to the slowest growing in terms of their growth rate. Right. So let's look at this first one: log base 4 of n plus log base 2 of n. Now we want to essentially erase the bit that is not being that is being dominated, right? So in this case, we want to know, okay, which is dominating which, log base 4 or log base 2? So by using just a bit of mathematics, we can use the change of base formula to convert logarithm's base number to anything we want. So specifically, the change of base formula works like this: log base b of x equal to log base d, and d can be any number of x divided by a log base of the same number of b. So in other words, what we can do is we can change this log base 4 of n into log base 2 of n divided by log base 2 of 4. And log base 2 of 4 is just 2. So essentially, this bit right here that we're putting in the denominator is just a constant. And remember, when we're doing these kinds of analysis, we're ignoring all the constants. So essentially, what we can do is we can ignore it completely, and we can say that log base 4 of n is approximately log base 2 of n. And it turns out that we can convert a log of any base into another log of any base. And so what we generally do is just anything, log base anything is just going to be in complexity of log. All right. So that's why we see omitting the bases altogether, because we can just convert them using the change of base formula. So ultimately, this is what we get by doing, a quick change of base mathematics. We get 3.5 times log base 2 of n. And when we convert to the big O bound, as in we drop all the constants, we get O of log of n. All right, and then the next few ones are a little more straightforward. N over 2 plus 4, we erase the constant 4, and since it's just essentially half times n, we drop that as well. So it's going to be n, which is in big O of n. 2 to the n over 3, erase the constant 3, that's going to be 2 to the n. 750 million. And now remember here, since 750 million has absolutely no relation to n, as in an increase of n doesn't change the value of 750 million, this essentially becomes a constant. Because remember, when we're thinking of n approaching infinity, these numbers are considered super small. Like 750 million is minuscule compared to what we're going to be dealing with. So this complexity is just going to be O of 1. All right, lastly is 8n plus 4n squared. We see that n squared is a higher order polynomial, so it dominates 8n. and we erase it completely. And since we're dropping the constants, it's just going to be n squared in terms of the complexity. All right, so now we're going to be ordering from the fastest growing to the slowest. Now, I want to be specific here. When I say fastest growing, it means that it increases the most as n increases. So in terms of the runtime, it's actually slowest to fastest in terms of the runtime if we would run code with these kinds of complexities. All right, so the fastest growing would be an exponential. So we have here 2 to the n. Following an exponential would be a polynomial of high degree. In this case, we have O of n squared, and then O of n, which is a polynomial of order 1, followed by log of n, followed by a constant. All right, yeah, and just a quick note that complexity class, a code that takes complexity class of exponential takes really, really long to run, because if you think about it, if n is, let's say, just 10, that output would be around, more than 1,000. So yeah, try to refrain from writing code that is an exponential complexity. All right, now we're going to be doing 1b. So let's start with this first one, 2 to the power of n over 2. Is it its own complexity, right? Or is it part of 2 to the n? So it turns out that even though it seems that way, if we do a little math again, it doesn't actually work. So let's give an example right here. And I want to note that 2 to the power of n over 2 is just 2 to the power of half n, right? So now let's take a different sort of constant in the exponent. Instead of half, we're going to put 2. And note that 2 to the power of 2n is the same as 2 to the power of n times 2 to the power of n. Now we can't just drop one of them, because let's suppose that, let's consider a different example where this is n times n. We can't just say that n times n is n squared, right? We can't just say that n squared is the same with n. So that's why we can't really combine these together. And so this becomes different. So the constant in the exponent cannot be removed. So it turns out that 2 to the n over 2 becomes its own complexity class. All right, the next one, 3 to the n, no constants to drop. So that's literally just 3 to the n, a different complexity class entirely, followed by 2 to the n, which is, the same thing. It's its own complexity class, 2 to the n. So now we're going to be sorting which of this is the fastest growing to the slowest growing. So the answer is going to be 3 to the n, followed by 2 to the n, followed by 2 to the n over 2. A general rule of thumb is that if you look at the base first, a higher base will always lead to a faster growing function. If we have two functions of the same base, for example, here we have 2 to the n and 2 to the n over 2, now we look at which constants on the exponents are smaller.